Hello, young scientists. Welcome to an exciting journey into the world of work and energy. Today, we're going to explore these fascinating concepts that are not just confined to your textbooks, but are all around us, influencing everything we do. Today, we're diving into the exciting world of work and energy. These concepts are the backbone of many scientific principles, and are crucial for understanding how the universe operates. These concepts are everywhere in our daily lives. Think about the simple act of walking in the park or playing on the playground. Every step you take, every jump you make involves work and energy. From riding a bike to switching on a light, it's all about work and energy. When you pedal your bike, your muscles are doing work, and that work is converted into energy that moves the bike forward. Work and energy are fundamental concepts in physics. They form the basis of many laws and principles that explain how things move and interact. For instance, the famous equation E=mc² by Albert Einstein is all about the relationship between mass and energy. They help us understand how objects move and interact with the world around them. When you see a car driving down the road or a pendulum swinging in a classroom, you're witnessing the principles of work and energy in action. Whether you're a budding engineer, a curious mind, or just love to understand how things work, understanding these concepts will give you a whole new perspective on the world. Imagine being able to explain why a roller coaster speeds up as it goes downhill, or how a rocket launches into space. So, buckle up, and let's get energized about work and energy. We're going to explore real-life examples, conduct fun experiments, and dive deep into the science that powers our everyday lives. Get ready to see the world through the lens of physics, and discover the wonders of work and energy. In everyday language, work might mean doing your homework or chores. For instance, you might think of work as the effort you put into studying for a test, cleaning your room, or even helping out with household tasks like washing dishes or vacuuming the living room. These activities require effort and time, and we often refer to them as work in our daily conversations. But in physics, work has a specific meaning. It's not just about effort or time spent. In the realm of physics, work is a well-defined concept that involves both force and movement. This scientific definition helps us understand how energy is transferred and how objects interact with forces in the physical world. Work is done when you apply a force to an object, and that object moves a certain distance in the direction of the force. For example, if you push a shopping cart at the grocery store, you're applying a force to the cart, and as it moves down the aisle, you're doing work on the cart. The key elements here are the force applied and the movement in the direction of that force. Imagine pushing a heavy box across the floor. This scenario is a classic example used to illustrate the concept of work in physics. When you push the box, you're exerting a force on it. If the box moves in the direction you're pushing, then you're doing work on the box. The heavier the box and the further you push it, the more work you're doing. You're applying force on the box, and it's moving in the direction you're pushing. That's work. This simple example helps us grasp the fundamental idea that work involves both a force and a displacement. Without movement, no work is done, even if you're applying a force. We calculate work using a simple formula. Work equals force times distance. This formula, often written as W equals sine FXD, allows us to quantify the amount of work done in any given situation. By knowing the force applied and the distance over which it acts, we can determine the work done. The unit of work is joules. Named after the physicist James Prescott Joule, this unit helps us measure and compare the work done in different scenarios. Whether you're lifting a book, pushing a cart, or moving a box, the work done can be expressed in joules, providing a clear and consistent way to understand the energy involved in these actions. Now, let's talk about energy. Energy is the ability to do work. Think of it like this. You need energy to do work, whether it's pushing a box, lifting weights, or even just standing up. Energy comes in many forms like kinetic energy, potential energy, heat, light, and sound. Kinetic energy is the energy of motion. Anything that moves has kinetic energy. The faster an object moves, the more kinetic energy it has. The heavier an object is, the more kinetic energy it has at the same speed. Imagine a speeding train. It has a lot of kinetic energy because it's heavy and moving fast. The formula for kinetic energy is kinetic energy equals 1/2 times mass times velocity squared. Section 5. Potential energy, stored energy. Potential energy is stored energy. It's the energy an object has because of its position or state. Think of a book held above the ground. It has potential energy because of its position relative to the ground. This is called gravitational potential energy. A stretched rubber band also stores potential energy. The formula for gravitational potential energy is potential energy equals mass times gravity times height. Section 6. The law of conservation of energy. Now here's a fundamental law of physics, the law of conservation of energy. This law states that energy cannot be created or destroyed, only transformed from one form to another. Think of it like a game of energy transformation. Energy is constantly changing forms, but the total amount of energy always stays the same. Section 7. Transformation of energy, from one form to another. Let's look at some examples of energy transformation. When you drop a ball, its potential energy is converted into kinetic energy as it falls. When the ball hits the ground, some of its energy is transformed into sound and heat. In a hydroelectric dam, the potential energy of water stored at a height is converted into kinetic energy as the water falls, which then turns turbines to generate electricity. Section 8. Calculating work and energy, numerical examples. In this section, we will delve into the practical applications of the concepts of work and energy by solving some numerical problems. These examples will help solidify your understanding and give you the confidence to tackle similar problems on your own. Let's solve some problems to see how we can calculate work and energy. By working through these examples, you'll see how the theoretical concepts translate into real-world scenarios. This will not only enhance your problem-solving skills but also deepen your appreciation for the subject. A person lifts a 5-kilogram box to a height of 2 meters. This simple action involves the concept of work, which is a fundamental idea in physics. When you lift an object, you are applying a force over a distance, and this is what we refer to as doing work. How much work is done? To find this out, we need to use the formula for work. This formula will help us quantify the effort involved in lifting the box. Solution. Work equals force times distance. This formula is derived from the basic principles of physics and is essential for solving problems related to work and energy. Force equals mass times gravity, where gravity is 9.8 meters per second squared. This relationship is crucial because it allows us to calculate the force exerted by the box due to gravity. Force equals 5 kilograms times 9.8 meters per second squared, which is 49 newtons. By multiplying the mass of the box by the acceleration due to gravity, we get the force in newtons. Work equals 49 newtons times 2 meters, which is 98 joules. This means that the work done in lifting the box is 98 joules. Joules are the units we use to measure work and energy. Now let's consider a different scenario. A car with a mass of 1,000 kilograms is traveling at a speed of 10 meters per second. This example will help us understand the concept of kinetic energy, which is the energy an object possesses due to its motion. What is its kinetic energy? To find this, we need to use the formula for kinetic energy, which takes into account both the mass of the object and its velocity. Solution. Kinetic energy equals 1/2 times mass times velocity squared. This formula is fundamental in physics and helps us calculate the energy of moving objects. Kinetic energy equals 1/2 times 1,000 kilograms times 10 meters per second squared, which is 50,000 joules. This calculation shows that the car has 50,000 joules of kinetic energy due to its motion. Understanding these concepts is crucial for solving real-world problems in physics. Section 9. Conclusion, work and energy in our daily lives. Work and energy are everywhere. From the food we eat to the cars we drive, understanding these concepts helps us appreciate the world around us. Next time you see something in motion, think about its kinetic energy. When you see something at a height, think about its potential energy. Remember, energy is never lost, only transformed. So, keep exploring, keep learning, and stay curious about the amazing world of science.